So our last objective is similar to what we did with population proportions. We are going to determine the sample size that's required to obtain a certain level of confidence for a specified margin of error. So researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like to they would like their estimate to be within 1 milligram per deciliter of the true value of mu at 95% confidence level. A previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Obtaining monkeys is time consuming and expensive, so the researchers want to know the minimum number of monkeys they will need to generate a satisfactory estimate. So what they've given to us is they've given us the level of confidence, 95% confident, and they've given us the margin of error that they want. They want to be within 1 milligram per deciliter. So they want our margin of error to be plus or minus 1. So we have to figure out what sample size do we have to ensure we have at least a point one or a margin of error of 1. What I've done is written down all the information they gave us. We have a 95% confidence interval, and they also gave us from a previous study the estimated standard deviation of their cholesterol levels. So since this is the case, we have a good estimate of the standard deviation for the population, and that means we're going to actually use a z interval instead of a t interval. And the reason is because think about what you have to create a t interval. You have to have a sample size in order to get the correct degrees of freedom. Well, we don't know what the sample size is. The sample size is unknown, is what we're trying to solve for. So since we don't have a sample size, we can't use degrees of freedom to estimate a critical value. We have to use a z distribution in order to figure out the solution to this. So our margin of error is going to be using a z instead of a t critical value. Our margin of error will be the z critical value times the standard deviation of the statistic, which is the population standard deviation divided by the square root of the sample size, which the sample size is the only unknown. And they want this to be within, so less than or equal to 1 milligram. So we'll set this less than or equal to 1 milligram. I've set it less than or equal to 1. So now all I have to do is plug in my critical value and my standard deviation, which my standard deviation I know is 5. And then since it's a z critical value, I'm not doing inverse t, I'm doing inverse norm again. And we should know for a 95% confidence interval, the critical value is going to be 1.96. Just in case you forgot how, this is the reason that our critical value is 1.96. I'm finding the 2.5th percentile of the z distribution. So the mean is 0, standard deviation is 1, no degrees of freedom for this one. Now I will use algebra and solve for the square root, or solve for n, and that will tell us our sample size. So divide both sides by the square root of n to cancel the square root of n on this side, and then when we get it over here isolated, we're going to square both sides, and we get n has to be greater than or equal to 96.04, which means to have a margin of error that's guaranteed to give us at least 1, we have to have 96.4. So we have to include this 0.04, and we can't have 0.04 of a monkey, so we have to have 97 total monkeys to ensure this. So our sample size needs to be 97 monkeys. The key to this problem is you have to realize that you're using a z critical value for this margin of error because you don't have a sample size, so you can't find a t critical value. This is the best estimate that you can use.